Hi science students. In this video we're going to discuss conservation of momentum. We are familiar with the concept of momentum from Criterion 5. However, within Criterion 6 we start to examine momentum from the perspective of collisions and explosions. So I'll show you some examples of those shortly. But if you want to pause the video and take down these notes, I'll give you an opportunity to do that, and then I'll discuss these with you. So go ahead and pause and take these notes down. Okay, so as I mentioned, what we're discussing here is principally conservation of momentum in collisions. So when two bodies collide, and we're only going to discuss situations with two objects that are colliding. Yeah, similar to something like this. And in addition to that, we need to consider and have an understanding of explosions. So there might be a body like a bomb, and it's sitting still on a surface, and all of a sudden it explodes, and it sends fragments in all directions. Now in real life, of course, it's most likely that the bomb will split up into many dozens, if not hundreds and thousands of fragments. However, we're just going to consider a simplification where a bomb type object or an explosive type situation sends two fragments in opposite directions, most likely in opposite directions anyway. Okay, so going back to these notes, the important concept is that before the collision or explosion, the objects will have a combined momentum, and that combined momentum will be conserved after the collision. So momentum is mass times velocity. Here you can see that I've got two MV calculations occurring at the same time. This one I've just got the hand on, or next to, that cross there. That would be the mass multiplied by the velocity, hence the momentum of the first object in the collision or explosion. And then this next calculation, that one there that I've got the hand next to, or the cursor, would be the mass by the velocity of the second object that's involved. And we add those up together, okay? And so that's the momentum of the second object combined with the momentum of the first object. Of course, this assumes a closed system, so there's no energy lost to outside sources such as heat, sound and friction. So in all of these situations we ignore those factors, I would say just about always. There may be exceptions to that, but you wouldn't be required to do calculations, I'd expect. Anyway, let's have a look at an example of how we do these. Okay, so this is in your notes. We have two objects. The big blue object, 2.6 kilograms, is traveling east, which is pretty much to the right of this screen or this presentation, at 8 meters per second. And now just see here, we've got a thing saying 1.8. Oops, I'll just change that here. Well, that's going to be 1.6 kilograms. So I'll just make a little change because that's what's in the notes below. So in fact, actually, no, I won't do that because the calculation there has a 1.8 here as well. So sorry about that, guys. I'll have to fix that up, but that should be 1.8 and 1.8 there. We'll just change those. Okay, now this 1.8 kilogram object is traveling to the west. Okay, so they're traveling in opposite directions, and obviously they're going to collide with one another. Okay, so what we're going to do is consider before and after. So this is before they collide, and this is after they collide. Okay, so we have the masses here. Let's fill in the blanks, and you might want to pause and fill in these blanks on your own first. I'll give you an opportunity to do that if you want to. So you go ahead and do that, and then I'll catch you up. Okay, so the mass of object 2 is 1.8 kilograms. Now, the velocity of object 2 is given here. You can see that it's negative 3.5 meters per second. Okay, so that means that the blue object is traveling in the positive direction, and I've set east as positive in this case. So we're working with the easterly direction to be positive. So that means that the velocity of object 1, the blue object, is positive 8 meters per second. Okay, and that pink object is traveling to the west, so that's in the negative direction. Okay, so let's calculate the momenta of these. So we multiply mass by velocity. So for the larger blue object, it's 2.6 by 8. And for the smaller red object, it's 1.8 by negative 3.5. So we're going to calculate each of those. Now we could calculate them and separately and add them up, but I'll just do it in one go. So the total momentum, P before, and I'll just squeeze it in here. I haven't left much room here, but I'll do it here. So P, the momentum before, is equal to 2.6 by 8 plus 1.8 by negative 3.5. So that's the calculation we're going to do. So if we put that into the calculator in one go, 2.6 by 8 plus 1.8 by negative 3.5, and we get 14.5 kilograms meters per second. So if we combine those two, that's the total momentum. And obviously that must be to the east. So although this system has one object with its momentum traveling to the east, and the smaller object has momentum in the westerly direction, the momentum of the big blue object, 2.6 by 8, it's contributing 20.8 towards the east, right? Now the smaller object, 1.8 by negative 3.5, it's contributing negative 6.3, and that's to the west. So we see that the bigger object is cancelling that momentum out, and overall most of the momentum is to the east, if you get my drift. Okay, now after the collision, the momentum is still this number. Okay, so P after the collision is equal to 14.5 kilograms meters per second to the east. So what we do is we equate that with the mass and velocity of the two objects afterwards. Okay, so I'm going to write it out a little more explicitly this time. So P after is equal to m1v1 plus m2v2. Now, of course, I'll just highlight this so we can see where each thing's coming from. So this is coming from the blue object, and this one is from the pink object. Okay, so we're going to substitute the information that we know. First off, they tell us that after the collision, the smaller mass, so that's the pink guy, yep, I've got my right highlight here, the smaller mass moves off with a velocity of 5 meters per second east. So that means we know that this object bounces back in the opposite direction at 5 meters per second to the east. Right, so let's put in the information we know. We know the momentum is still 14.5. We know the mass of object 1 is 2.6 kilograms. We don't know velocity 1, so I'm just going to leave that and multiply by v1. That's what we're actually going to rearrange to calculate. Plus, now mass 2 is still 1.8 kilograms, and the velocity we're told is 5 meters per second east, so that goes in as a positive 5. So now you might want to pause the video and see if you can rearrange to get v1 on its own and find out what the velocity of the larger object is. Okay, so if we rearrange this, you should get that V1 equals, now I'm going to take that 1.8 by 5 over first and subtract it, so 14.5 minus 1.8 times 5, and then this is multiplying this 2.6, so it goes over the other side and it divides. So with your rearranging, you should get something similar to this. Alright, so get that fraction going. Whoops. So 2.11. Is that right? 2.12, sorry, to three significant figures. Now, what direction does the blue object travel in? Well, the fact that this is positive means it's in the positive direction, which is east. So after the collision, the blue object continues to travel east at 2.12 meters per second. Okay, so that one's done. Now, these do take a bit of time to get your head around, so you might want to stop there and have a look at some questions that are more similar to this one. And this is what we would term an elastic collision. Okay, we'll talk more about elastic versus inelastic later, but I'm going to do this example below where we have an inelastic collision. So the first one is elastic, and here is inelastic. Now, if you want to pause the video and go and try a few questions like the one up top and then come back later, please do that. I'm going to continue on in this video and solve the second problem, and that's if the objects were to stick together. Now with this one, I suppose the distinction is like the one up above is probably a bit more like a game of, say, pool, where the balls tend to knock into one another and make a clicking sound, and they bounce off one another really effectively. This down here is, we're considering perhaps that these aren't hard objects. There may be a couple of lumps of plasticine that collide and stick together or something like that. Okay, so a different type of situation. All right, so we know that the momentum before is 14.5 kilograms meters per second east. So of course, after the collision, that continues. So these objects will move to the east with that momentum, 14.5 kilograms meters per second. What we want to know is, if they stick together, how fast do they go? So we could set it up like this. So we know now that P after is equal to, now what I can do is I can combine the masses like that. I'm going to add them together and multiply them by this velocity that they would move off with afterwards. So 14.5 is the momentum. Then we've got the two masses, 2.6 plus 1.8, and we multiply by the velocity. So if you rearrange this, you'll get 14.5 on those masses combined. So that's how we can handle those situations where the objects stick together. So in this case, 14.5 over 2.6 plus 1.8 gives 3.3 if we go to three significant figures. 3.3 meters per second. And because that's positive, once again, we know that must be to the east. So if those velocity calculations, if the answers come out negative, then you know that it's in the negative direction. But these both came out positive, so must be to the east. Okay guys, so check the description for the video. These do take a bit of practice, but if you look at those questions in the description, you'll get some really good practice on these types of momentum questions.